This video has been supported by Tektronix. Hey guys, are you up to date? In the last video we've repaired and rejuvenated a Fluke 5700A multifunction calibrator, or ruined what was left of it. Today we are going to determine which and how much, with the help of a majestic Keithley 2002. Tektronix was kind enough to send that over just for this purpose. But since the opportunity to work with Keithley's highest resolution multimeter doesn't present itself all that often, I'd like to give you a little tour first. First and foremost, this is of course an 8.5 digit multimeter, the king or queen of the 2000 series. It has a nanovolt resolution in the lower DC voltage ranges, which on its own doesn't mean all that much. At least 4 other meters in this shot can display nanovolt. What counts are the more subtle properties of Keithley's custom ADC: noise, stability, linearity, and useful sample rate. The latter, also known as DCV measurement speed, is a really important parameter. It can be configured to whole numbers of power line cycles, or presets like fast or high accuracy. High accuracy means 10 power line cycles or about 200 milliseconds per 8.5 digit reading where I live. That's what they recommend to achieve the uncertainties specified in their datasheet, plus another digital filter that displays the average out of every 10 readings. Bottom line, we are looking at about 2 seconds per high accuracy reading, whereas Solartron 7081 needs almost a minute. Both of these meters are synchronized to the mains frequency, so that the positive and negative half waves of power line interference cancel each other out, or at least every reading gets the same amount of power line interference. Other than that, no schematics or anything have been released for the 2002, so I can only guess based on internet rumors what makes it good. This is a simplified version of what I think their analog to digital converter looks like. It's based on a programmable logic device and a stable clock signal. For a specified time, they let the voltage to be measured charge a capacitor via a precision resistor, only to discharge it again via one of multiple precise current sources. In a perfect world, the time it takes to discharge that cap would only depend on the initial input voltage. If you ever find that perfect world, let me know. But while we are stuck here, it's an absolute marvel that they managed to make this circuit work so well, in spite of jittery clocks, drifty resistors, leaky caps, and analog switches that behave differently from one another and from time to time. Look, even my simulation consisting of purely ideal components somehow manages to have noise. The 3 different rundown current sources are what give this arrangement its name, multi-slope ADC. They are derived from an LTZ1000 in this multimeter. That way it inherits the famous stability of that part. And I can confirm that now with a measurement of my calibrator set to 10 volt for 4 days straight, including some harsh climate conditions in my apartment. These are all pretty good results within roughly 1 ppm. The blue trace, Solartron 7081, is going a bit crazy in the first half, because I've disabled its internal drift correction in favor of low noise. But the green trace, representing Keithley 2002, is the most stoic, in spite of being exposed to the same ambient temperature swings as the others. Pretty good. Speaking as a connector purist, there's only one thing I don't like about the 2002. It's recessed shrouded banana jacks. I got some special Pomona low thermal EMF test leads for these, but not sure if those are even necessary. It's probably all fine for measurements above nanovolt, but man, would I be thrilled to see a successor with copper binding posts. Otherwise, no surprise, I really like the 2002. It's the smallest and lightest multimeter of its caliber. It has a beautiful 2-line alphanumeric display, and the user interface as well as the GPIB language are exactly the same as for the 2001, so I didn't have to learn anything or rewrite my software. It's quiet too, not completely silent, there is a little cooling fan, but I could definitely work in its vicinity all day long. Unlike my Fluke 5700 hairdryer. Listen when I wake it up. No kidding, nothing can really work in its direct vicinity. Its hot exhaust would scare away all the precious ppms in neighboring test equipment. That's why it has to live on the ground for the time being. The 2002 has a relative internal temperature sensor, with which it can tell the difference between its momentary internal temperature and the one it had during calibration. 2001 doesn't have that, I just checked. Both DMMs can read the most common types of thermocouples and resistance thermometers, with a fantastic millikelvin resolution. To determine the absolute value of a thermocouple reading, it would have to add the reference junction temperature, which would be the front input connector temperature in this case. They don't seem to have sensors there, so absolute thermocouple measurements are only possible with the appropriate thermocouple scanner module, which can be plugged into the rear. Not a big deal, I think. In precision applications, platinum resistance thermometers are the way to go anyway, and for those the absolute readings are included, of course. Whatever it is you want to measure with the 2002, be it temperatures, voltages, DC, AC or resistances, there's always data storage and a sophisticated set of math operations available to determine often needed values like min, max, average, standard deviation and more, without involvement of a computer. Alright, let's get on with what we are here for. Of course, computer involvement is where we are heading in a moment, to plot data over a longer time and to verify that the 5700 is working more than temporarily. I'm also setting up my own 8.5-digit meters to come along for the ride, but those haven't seen a calibration in years and are nowhere near as trustworthy as a latest generation 2002 straight from the manufacturer. I was a bit sad when that turned out to be just out of Cal too, when it arrived here July the 16th. Otherwise I could have adjusted the calibrator ranges manually to match Keithley's, and from there inherited the quasi-traceable accuracy to all my other meters. Oh well, as long as we can verify stability and linearity, we can always import the absolute accuracy later. While everything is still warming up, I'm making some momentary measurements over 10 power line cycles, with a repeating averaging filter that starts over every 10 measurements, and manual triggering so that I can make adjustments on the calibrator at my own pace. Well, the two champions don't agree perfectly, and that's no surprise after such extensive repairs and renovations. But I'm getting similar results, which is the most important part here. I can now use the rotary encoder to fine adjust the output and show how far apart the two devices are. Approximately 0.0044% in this case. That's 44 ppm, very unseemly under normal circumstances. All the current ranges seem to be perfectly stable at a glance, all the way from microampere to the highest 2 ampere current range, which still has that cracked resistor network. Now for the voltage ranges, I do care about every last little nanovolt I can get, but somehow I've acquired yet another meter with recessed banana jacks, and I have only one pair of these Pomona low thermal test leads. Generally, these hollow ones are also regarded as pretty good in the low thermal EMF department, but these happen to be attached to a Solartron input cable. Luckily, I have another very reliable connector available. Ubiquitous Ethernet cable is usually shielded quite well, and the super thin pure copper data lines, in combination with some metrology grade Q-tips, make excellent low thermal EMF connections. When there is no thermal mass, any temperature difference won't last long. Whenever connecting two or more mains-powered devices like this, common mode voltages are a topic to keep in mind. The calibrator has a special blue output terminal called guard. That's not the same kind of guard we are used to seeing in Keithley's high-resistance, ultra-low current designs. In this case, it's a shield that surrounds the calibrator power transformer, as well as its appropriately named in-guard section. Since Keithley's inputs are not mains earth referenced anyway, I'm not using the external guard function in this case. Otherwise I would have connected the cable shield to guard on the calibrator side and to input low on the device side, to give common mode voltages somewhere to go, where they don't influence my measurements. Okay, I think every participant has warmed up now. The GPIB cables too, but they don't care. They are as stiff as always. But let's try anyway to get some automation going. Somebody gave me a hint about this awesome device, which is unfortunately no longer produced as far as I can tell. It's a GPIB to Ethernet gateway, and it looked even less remarkable in its original enclosure. I had to destroy that to satisfy my curiosity and find out how hard it could be to replicate such a thing. Oh, well, my conclusion is that Keysight makes something that does the same thing for $1,500. And of course you can always just use a standard GPIB to USB adapter. Not sure who's stiffer, the cables or me. Eventually, I want all my instruments connected and automated like this. I've started to make a minimalist multi-instrument data logging software for this. So far, I've only implemented my favorite multimeters. Notice how Keithley 2002 just inherits everything from 2001. These, in quotation marks, modern or not ancient devices are relatively easy to talk to. The commands understood by brown shoebox Keithleys from the 1980s, however, oh boy, those are absolutely cryptic and take a long time to implement. Here's my 237 SMU, for example. And here's the Fluke 5700, pretty easy. I'm using a new revision of an old acquaintance as a Raspberry Pi container, the Raspad 3 from Sunfounder. It's a bit of an overkill for just writing down the occasional 8.5-digit reading into a database. But it's quite a convenient mobile package for every project that would otherwise be a raw Raspberry Pi board, and an unmanageable nest of cables, two peripherals and monitor. This thing is the monitor, and we are going to set it up to keep an eye on our precious PPMs. Now, to use an ordinary USB GPIB adapter, you'll have to download and compile the Linux GPIB project, which needs kernel headers and more, and isn't even compatible with all of them. My lucky Ethernet gateway needs only the Python VXI11 package, and we are ready to talk to GPIB devices. We could immediately write data into CSV files. But I want something a little bit more fancy than that, so I'm going to install InfluxDB and Grafana. Those are pretty popular for data logging on the Raspberry Pi, so you can just follow tutorials on the internet. I also added periodic reading of two TMP117 I2C temperature sensors to my software. With their 8 millikelvin resolution, those are just the right kind of overkill for ambient temperature measurements during long-term experiments. Remember, this is how I used to document these long processes, just a GoPro in time-lapse mode. Primitive and hard to evaluate. Now I've got a Python script that sweeps the calibrator output voltage from -10 to 10 volt in 50 millivolt steps, while triggering and reading all 3 voltmeters once per step. The results, as well as temperature information, is saved in a time series database, from where it can be accessed by Grafana, for example. That's a really cool browser-based visualization software. Dark mode by default. Need I say more? My simple linearity tests, featuring 3 voltmeters and 3 thermometers, are really just scratching the surface of what's possible with Grafana. But hey, it's a huge improvement and a lot more insightful than the time-lapse, isn't it? I can use math operations in the database queries to turn the absolute voltage readings that are stored there into ppm deviations, for example. This reveals a number of things. First, my calibrator is doing well, and so is Keithley 2002, the yellow trace. It has the best linearity out of the 3 meters I've tested here. This inverted bell curve resembles typical results for that meter. Solartron 7081 isn't too bad either, albeit a bit noisy. Advantest R6581T has a bit of an ugly zero transition. I haven't had a close look at that one yet. Maybe we can fine-tune it a bit. But that's it for today. Mission Calibrator Rescue has been a huge success. Thanks to Tektronix for helping me verify that. And a huge thanks to my PTB friends for making all this possible in the first place.